So let's start this lesson by reviewing some methods we've learned to solve polynomial functions so far. Well, we've learned two. We've learned factor out a greatest common factor. Right, and then if we had anything, any expressions, the expression that was left, if that had an exponent higher than just an x, we combined that with factoring quadratic. Right, but the main technique was factoring out a greatest common factor, and then we used this for the leftovers. We also learned factor by grouping. And then we also had to factor quadratic often with that one. Sometimes we couldn't factor, right? And we had a sum of squares. And then we had to take a square root of both sides. We're going to learn two more solving techniques. I don't know if they'll both be in this podcast, but one of them involves the rational root test to narrow down our choices of possible solutions and then using long or synthetic division. And then the other is a technique called substitution. So let's get started with the rational root test and learn what that is and how that can help us. All right, so solving polynomial equations. All right, so choice number one, try to factor a common monomial out first. You're going to factor what's left, or if you can't factor, then you're going to use solving by taking a square root or completing the square or quadratic formula to solve if reducing by a common monomial leaves a trinomial term with an exponent. Right, so a trinomial doesn't mean a term with an exponent, but a specific trinomial that we're going to have to do a little bit more work with is a term with an exponent. So if we have a term left with an exponent, we're going to have to do some more work to solve for that variable. We can also use factor by grouping if we can factor the same term out of a pair of terms, leaving a common binomial. But remember, we must have four terms to use that technique. The two we're going to look at today, if you can't reduce, then you can use the rational root test to determine possible roots. And then you'll use synthetic or long division to find the actual roots, and then factor and solve. And then if the polynomial has three terms, and the exponent on one is twice that of the other, we can also use a technique called substitution. Let's first of all look at the rational root test, and then we're going to try solving with that. So the rational zero test, or rational root theorem, says that if a polynomial f of x has integer coefficients, every rational zero of f has the form the factors of q divided by the factors of p. So in other words, any rational solution we have has to be the factors of our constant term divided by the factors of our coefficient of the leading term. Now p and q are just used as way to label it. But they don't really have any specific meaning other than remembering that it's going to be the constant, factors of the constant over factors of the leading coefficient. So you can just remember it like that. So let's look at our first example. We want to find the rational zeros of f of x equals x to the fourth minus x cubed plus x squared minus 3x minus 6. So now, the rational root test, there's an infinite number of choices for me to choose from. How do I know which one to choose? Well, the rational root test says the number you should choose is going to be has to be from the pool of numbers that you can write using the factors of your constant term divided by the factors of your leading coefficient. Right? So the constant term here is -6. The factors of -6 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Factors of the leading coefficient, just plus or minus 1. So those numbers aren't going to change at all if we're just dividing by positive or negative 1. Right? We'll still have the same number of choices. So out of all the infinite number of numbers there are, there's only 8 possible choices for our rational roots, right? Our rational solutions, right? And that's going to be plus or minus, +1, -1, +2, -2, +3, -3, +6, -6. That's it. That's the only choices. Those are the factors of our constant term divided by the factors of our leading coefficient. All right, so when we're trying this, right, there's a little bit of trial and error. I mean, we have our list narrowed down quite a bit to just 8 possible solutions, right? But it may be that our choice doesn't work. Right? And so I wanted this to be as realistic as possible. I did not write down the choices because I want you to see. Sometimes you try something and it doesn't work. I'm just taking a little hunch here of trying 2. I got a lot of 1s there, and then I noticed, okay, 6 is twice as big as 3. Maybe 2 would be. Right? So it's not any kind of scientific thing. Ooh, if one term, you got a bunch of 1s as coefficients, and then you see one of them is twice the other. 2's got to be a solution. No. That's certainly not going to work all the time. But I'm just kind of like trying to figure out of my 8 choices, which one maybe seems like it could be it. All right, so now I'm going to write my equation using all the coefficients, and if anyone's missing, right, we're going to represent them with a 0. But we got our x to the 4th term, we got our x cubed, we got our x squared, we got our x, and we got our constant. All right, so now to use synthetic division, I bring down the 1, then I multiply. 1 times 2 is 2. Then I add, I get 1. 1 times 2 gives us 2. I add, I get 3. 3 times 2 is 6. -3 plus 6 is 3. 3 times 2 is 6. And then we add that equals 0. So 2 was a solution, or you can think of it as x plus 2 was a factor, right, of our equation here, x to the 4th minus x cubed plus x squared minus 3x minus 6. All right, so now let's rewrite this. So this is our constant. This is, this is our remainder constant x squared, x cubed. So that would be x cubed plus x squared plus 3x plus 3. Notice the first 2 terms have a coefficient of 1. Second 2 terms have a coefficient of 3. Maybe factor by grouping would work here as our second technique. Let's try that. All right, so the first 2 become a group. Don't forget plus in between. We're just rewriting it. We're not changing anything about it. And the second 2 become a group. Now we're factoring something out to rewrite this as a product. Right? So x cubed and x squared are both divisible by x squared. And then we'll divide. X cubed divided by x squared is x. X squared divided by x squared is 1. Right? So 3x and 3 are both divisible by 3. 3x divided by 3 is x. 3 divided by 3 is 1. So notice we have a common repeating binomial there. If we factor that out, we have x plus 1, and then we have the leftovers, x squared plus 3 equals 0. Right? So here you can see that 2 was a solution. Let's write that down. So I, by the way, included no there in case my choice was incorrect. So let's add the x equals 2. I forgot to do that earlier. And not only that is a solution, we have another solution now. We have x plus 1 equal to 0. Subtract 1 from both sides. X is -1. So now we have 2 solutions. Of course, we know there has to be 2 more because this is x to the 4th. Notice now we have an x squared plus 3. All right, so now that's not factorable. Sum of squares is not factorable. All right, so let's solve using a square root. So we'll subtract 3 from both sides. We have x squared equals -3. Right? And then we will take a square root of both sides. All right, so square root, and then don't forget plus or minus the square root. So we have square root of x squared is x equals. All right, so now we can simplify one thing. All right, so we can simplify the -1. Square root of -1, of course, is I. And then you can't do anything about the radical 3. So the rational root test does not tell us if we have complex solutions and what they are. It does not tell us if we have irrational solutions, right? But it does help us find our rational solutions. Right? So we have, let's continue writing. This is our real Right? And then our complex are x equals I square roots of 3 and negative I square roots of 3. And so these are the complex. So that means this graph would have two x-intercepts, right? Because it has two real solutions and then it has two complex solutions. And there we go. We're all done. So here we use synthetic division once and then factor by grouping and then solving by square roots. So you'll do that. You may use more than one technique, right? Because at certain parts of these problems, one technique's better than another. All right, we're going to use the rational root theorem, and we want to find the zeros, the solutions, of 5x cubed plus 14x squared minus 3x minus 2. All right, so our constant term is 2. Leading coefficient is 15. All right, so factors of 2, negative 2, are, I'll write it down here. So I'll put factors of constant. That's just going to be plus or minus 1 and plus or minus 2. And then factors of the leading coefficient. All right, so that's our leading coefficient is 15. All right, so we have plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. All right, so lots of different choices there. Let's write a list of all our possible solutions. Let me see if I left space over on the other page. I did. All right, so let's write it down there instead of over here. All right, so our possible solutions, okay, so we showed that we have plus or minus 1 and plus or minus 2 divided by plus or minus 1, plus or minus 3, plus or minus 5. Oops, that's supposed to be 5. And plus or minus 15. All right, so that means our possible solutions are going to be, so now we'll divide 1 by each one of those. So we have plus or minus 1, and we have plus or minus, look at that 1, or look at the plus or minus part. Plus or minus 1/3, because it's 1 divided by 3, and then plus or minus 1/5, and plus or minus 1/15. And then we have plus or minus 2, plus or minus 2/3, plus or minus 2/5, and plus or minus 2/15. Now I would not start off with the fractions, all right, for our and to find our solution. Let's start off with the integers. We have 1 and 2 look like the only integers. All right, so let's try, and then of course positive and negative. Let's try synthetic division with those. All right, we're not missing any terms. I don't know which one to take. Let's take 2. Negative 2. Let's take negative 2. X equals negative 2. Okay? So x plus 2 is the factor. All right, so we're going to have negative 2, and then 15, 14, negative 3, and negative 2. Bring down the 15. Then we multiply. 15 times negative 2 is 30. Then we add. We have 44. And we multiply. 44 times negative 2, that's negative 88. And you can see this is just not looking good for us whatsoever. All right, so let's write down our no's. So definitely negative 2. That didn't work out. Let's try another one. And I'm going to erase this. We don't really need to save it. All right, so let's try. All right, we tried positive 2. We tried negative 2. Let's try something smaller. Let's try maybe a 1. All right, and then we have 15, 14, negative 3, negative 2. All right, bring down the 15. 15 times 1 is 15. Add, we get 29. 29 times 1 is 29. And you can see this is not looking promising either. All right, so much for x equals 1. Oh, Oh, you know, when I was writing down the possible solutions, did I stop too? No, I didn't. Yeah, because it's our ending term doesn't have too many. Now, at first I thought I forgot to write something down, but I didn't. All right, so we've already tried -2 and 1. That's another reason that it's good to write that down, is you can look at who you tried. Let's try +2. We're running out of choices. All right, 15, 14, -3, -2. Bring down the 15. 2 times 15 is going to be 30. Oh, and that's not looking good either. All right, let's try -1. All right, so 15, 14, -3, -2. Bring down the 15. 15 times -1 is a -15. Add, we're going to get -1. Any day now. There we go. -1 times -1 is 1. Add, we get -2. -2 times -1 is 2. Add, we get 0. There we go. All right, so we got one solution, x equals -1. I should try that sooner. All right, and now we'll factor the rest. This is just a quadratic expression. Let's just use factor by grouping for quadratics. All right, so a times c. All right. Oh, I should probably write the question down, shouldn't I? Yes, I should. All right, so remainder, that 0 remainder tells us, right, that this is a factor. Constant x squared, so we have 15x squared minus x minus 2. Remember, setting that equal to 0 to solve. All right, so a times c is 15 times -2 is -30, and b is 1, right? Or -1. Right, so two numbers that multiply to give us -30, add to give us -1. Well, that must be -6 and +5. So we have, squeeze this in over here, 15x squared minus 6x, and then plus 5x minus 2. And the first two are a group, and the second two are a group. We'll pull out our greatest common factor. So 15x and -6x are both divisible by 3x. 15x divided by 3x is 5x. And then -6x divided by 3x is -2. And that's looking very promising. Only common factor for 5x minus 2 is a 1. And now we can factor that repeating 5x minus 2. And then we'll be left with the leftovers, 3x plus 1. All right, so let's write down our solutions here. All right, so we wrote down the x equals -1, right? And then we used factoring, and we got two more. So we have 5x minus 2 equals 0. So we'll add 2 to both sides, and then divide by 5. So x is 2/5. Notice that 2/5 is in our list someplace. There it is, right? But that's not the one we want to try, right? We want to try a rational solution. All right, and then our other one is 3x plus 1. And subtract 1 from both sides. 3x is -1. Divide by 3. X is -1/3. Right, and then we have all our solutions. So let's write them in the box there. So we have the -1 that we got by factor by grouping, synthetic division. And then we got two more, right, by factoring the quadratic expression. That was 2/5 and -1/3. And that's it, we're done with this problem. Not done altogether, just with this problem. All right, let's try this one. All right, so possible solutions are going to be the factors of our constant term divided by the factors of our leading coefficient. All right, so the constant term is 30. Right, so we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15. And of course, plus or minus 30. Right, and now we have to pick one. And notice, by the way, factor by grouping would not be a good choice here. we got, look at our coefficients, 1 and negative 8 and 23 and 30. Not anything really in common here. Let's try the 5. All right, so yeah, nobody's missing, so we're going to try 5. We have 1, negative 8, negative 23, and 30. Bring down the 1. 1 times 5 is 5. Added, we get negative 3. Negative 3 times 5 is negative 15, and that is not looking promising because we're going to end up with a really big number that doesn't cancel out the 30. All right, so, oh, I forgot to write that down. X equals 5 did not work. How about 10? Let's try 10. All right, so we have 10 and 1, negative 8, negative 23, 30. Bring down the 1. 1 times 10 is 10. Add, we get 2. 2 times 10 is 20. Add, we get negative 3. Negative 3 times 10 is negative 30. And we've got it. All right, and then we'll factor the rest. All right, so this is our remainder. This is our constant, our x, and our x squared. So this is x squared plus 2x minus 3 equals 0. And again, let's do factor by grouping. So 1 times negative 3 is negative 3. We need two numbers that multiply to give us negative 3. And add to give us our b term of 2. Of course, those would be, and multiply gives us negative 3. Add to give us positive 2, right, would be 3 and negative 1. All right, so we have x squared. We're going to replace that 2x with a 3x and a negative x. And the first two are a group. And then the negative x minus 3 is a group. We'll factor out a common factor, so factor out the x. When we do that, we're going to have x plus 3. And then divide by negative 1. So our two factors are the repeating x plus 3, and then what we get when we factor out the quadratic expression, which is x minus 1. All right, so now let's solve by setting those equal to 0. Right, so we have x plus 3 equals 0. X is negative 3. X minus 1 equals 0. X is 1. So in addition, our solutions, we have x equals 10. And then we have the ones we got by factoring the second part, which is negative 3 and 1. And there we go. Another one done. Let's see if we can do one more. It's getting a little late, but let's see if we can do one more. Oops. All right, so here's our next one. All right, and this will probably be a good place to stop after this one. All right, and then pick up with the next problem. We want to solve f of x equals x to the 4th minus 13x squared plus 36. We see we're missing an x cubed and missing an x. Right? So we're going to take the factors of our leading coefficient, our factors of our constant, which is 36, and divide that by the factors of our leading coefficient. Well, we got a few factors here, because 36 has a bunch of factors. So our possible solutions are going to be positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 6, positive and negative 9, positive and negative 12, positive and negative 18, and positive and negative 36. All right, so we have x to the 4th plus 0x cubed minus 13x squared plus 0x plus 36. All right, and so now we have to pick one. How about the 2? Right, so if we choose the 2, we're going to have 1 for the x to the 4th, 0 for the x cubed, negative 13 for the x, 0 for the, the x squared, 0 for the x, and 36. Right? We bring down the first term. 1 times 2 is 2. Add, we get 2. 2 times 2 is 4. Add, we get negative 9. Negative 9 times 2 would be negative 18. Add, we get negative 18. And then negative 18 times 2 is negative 36. There, that worked. All right, so the 0 here is the remainder, and then the constant x, x squared, and x cubed. So we have, let's write that, x cubed plus, and 2x squared. Almost forgot the 2. Then minus 9x. And then, minus 18. All right? So now I see this kind of pattern to our coefficients. Let's try factor by grouping. All right, so the first 2 are a group, and the second 2 are a group. And from x cubed and 2x, we'll factor out an x, and we'll be left with an x squared plus 2. And then from negative 19 and negative 8, we could factor out a negative 9, and we'd be left with x minus, factoring out a negative, so this would be x, where's my negative? There it is, x plus 2. All right, so now we have that repeating binomial, right, when we factored, and that told us that factoring worked, right? So we're going to have an x. Oh, oops, I'm sorry. I made a boo-boo writing this right here. So I left off a square. This should be a square, leaving this as, as x plus 2. There, that's much better. All right, so we have the repeating x plus 2, and then we have an x squared minus 9. Right, so that is a difference of squares. That's factorable. And if you remember from a couple podcasts ago, this will factor to x minus 3 and x plus 3. So our 3 solutions, we have x equals negative 2. We have positive 2 up here. We have x equals 3 and x equals negative 3. Right? So let's write our solutions. So x equals 2, negative 2, x equals 2, x equals 3, and x equals negative 3. Right? And so in the next podcast, we're learning another solving technique, actually specifically for this problem. Right? And then, let's see, we'll do a little bit more. We'll have 3, 4, 5, 6, 7, and so we have a few slides, 8 slides. This is what we'll do in the next podcast. Bye for now.